Welcome. In this lesson, we'll look at two more small signal models for the BJT, the R-Pi model and the RE model. You've already worked extensively with the H parameter model for analyzing BJT amplifiers. These new models give us alternative, often simpler ways to represent the same transistor behavior, depending on whether we view the device from the base side or the emitter side. Let's set the stage. You already know the H parameter model. The R-Pi model instead views the transistor from the base side, while the RE model gives a simple view from the emitter side. Both start from the transconductance Gm equals Ic over Vt. From this, Ic equals Gm times Vbe and Ib equals Gm over beta times Vbe. That gives R-Pi looking into the base equal to Vbe over Ib or beta over Gm, and Re looking into the emitter equal to Vbe over Ie, approximately 1 over Gm. The two are related simply. R-Pi equals 1 plus beta times Re. Here's the R-Pi model shown in two equivalent forms. On the left, the BJT is represented as a voltage controlled current source, a transconductance amplifier, where the collector current source is Gm times Vbe. On the right, it's shown as a current controlled current source, a current amplifier, where the source is beta times Ib. In both versions, R-Pi sits between base and emitter, defined as Vt over Ib or beta over Gm. These are just two ways of expressing the same base side view of the transistor. Now we add Ro to this model. Ro accounts for the early effect, the slight dependence of Ic on Vce caused by base width modulation. It's defined as Va over Ic, where Va is the early voltage. Ro is placed in parallel with the controlled current source between collector and emitter in both the voltage controlled and current controlled versions. This makes the model more accurate for calculating output resistance and gain in real amplifier stages. This is the RE model of the T model, an alternative to the hybrid Pi model that explicitly features the emitter resistance Re rather than the base resistance R-Pi. Again, there are two versions. On the left, a voltage controlled current source Gm times Vbe. On the right, a current controlled current source alpha times IE-Re is defined as Vt over Ie, which also equals alpha over Gm. The T model is especially useful when you want to view the transistor input directly from the emitter. Just like before, we can add Ro to the T model to account for the early effect. Ro equals Va over Ic, and it appears in parallel with the controlled current source between collector and emitter in both versions. The base emitter voltage and the emitter resistance Re still define the input side, while the control source either Gm times Vbe or alpha times Ie sets the output current. This gives us a complete small signal model ready to use in amplifier analysis. Let's apply this to an example. On the left is our amplifier circuit. Vcc equals 10 volts, Rc equals 3 kilo ohms, Rbb equals 100 kilo ohms, and Vbb equals 3 volts, biasing the base through Rbb on the right. We've replaced the transistor with its hybrid Pi small signal model, R-Pi in parallel with the control source Gm times Vbe connected between base, collector and emitter with Rc still in the collector branch. This is our starting point for finding the small signal voltage gain. Now let's work through the numbers. First, the DC bias. Ib equals Vbb minus Vbe over Rbb, giving 0.023 milliamps. So IC equals beta times IB or 2.3 milliamps, and VC equals VCC minus IC times RC, giving 3.1 volts. Next, the small signal parameters. RE equals VT over IE, about 10.8 ohms. GM equals IC over VT, 92 milliamps per volt, and R pi equals beta over GM, 1.09 kiloohms. The base emitter voltage divides down from VI by the ratio R pi over R pi plus RBB, giving about 0.0111 times VI. Finally, VO equals negative GM times VBE times RC, which comes out to negative 3.04 times VI. So the voltage gain AV equals VO over VI or negative 3.04 volts per volt. This example demonstrates how to analyze amplifiers using the R pi model. Work out a few examples given in textbooks to understand these models better. With this, we have come to the end of the lesson. Thank you.